Testing, testing. All right, you guys. Oops. Sorry, Zoom is not cooperating with my hardware very well this semester, but I think it's working. All right, guys, welcome back. So listen, let me turn straight away to the exams. You guys had some interesting questions and comments after we met last time. So I talked to the Quest people. They told me some things I was supposed to click to make the your grades and the solutions available to you. Have you guys gone back to Quest to see if you can get more information about exam 2 than you had on Monday? Was anybody able to see the explanations of the answers? They're available. Okay, good. Thank you. All right, so the rest of you, if you want to go see, you should be able to get the information there. And I believe you also now have the papers coming back from the free response questions. That should be through Canvas. And I imported it all into a spreadsheet last night to get a sense of the curve. You all did pretty well. It was a good, I guess it was a good exam because the average score was like 80 something, which is pretty high for one of my tests. There will be just a little bit of a curve. For most people, the 90, 80, 70 scale will tell you just what your letter grade is for this, this exam. At the low end, you're a little better off if I use the mean and standard deviation. I'll have a precise curve floating around, I guess probably tomorrow. But anyway, most of you I think did pretty well. About, I don't know, 20% of the class has an A+ from the exam, so that's good. There's that, and then of course I will remind you again, the situation for this semester is you guys can just keep plowing through, doing your best in all of your courses. I will assign grades according to the mechanism that I initially proposed in the syllabus in January. If you don't like your grade, you can change it to pass-fail after the grades come out, or you can Q-drop the course after the grades come out. So I don't think, most of you don't really have anything to worry about. I think your grades are good, but if you are concerned, we can talk about it a little bit more, maybe in office hours. So there's that. That was one of the things that I asked the Quest people. I also spoke to them about getting PDFs of your questions if you sit down for another exam like this. And they pointed out that actually that's kind of hard. I can't prepare a PDF for you in advance because you guys get randomized questions. And so the exact questions that you're going to get will be different from the ones that your neighbor is going to get. So I asked if the machine could generate them, and they said they're working on that. That's all I could get. And then I got the same response when I said, is there some way to restructure it so that you could kind of tentatively input questions to each one of the, input answers to each one of the questions, and then only have a final submit at the end of the whole thing. And they said there's some known bug in their system that's preventing that from working right now, but they have some people looking at that. So in the future, I guess I just have to warn you that as you try all of the questions, you can work on the questions individually, but once you actually submit your answer to any one of the problems, you can't go back later and unsubmit it. So just keep that in mind when you're answering the questions. As it turned out, I looked at the statistical analysis, and it seemed like the first couple of questions were ones that you all did pretty well on. So I guess as long as you got the pattern early on, then you probably didn't have anything to worry about on the grades. And I think that was all I was supposed to look into for the exam. Were there other things that you guys wanted to ask me or tell me about the midterm? No? Okay. Then there's, yeah, go ahead.
Can I ask you a question in regards to the final?
Yes, sure.
Okay. So I'm assuming it's going to be the same format as how we did midterm 2?
Yeah, probably.
Yep.
Yep.
Okay.
Well, is there something that you need changed?
No, I just wanted to make sure that was very clear. I know you talked about it in parts, but so it's going to be still, we have some questions that are pre-response, and then we'll have a portion that's within the time frame of 24 hours, but once we start, we have a set amount of time to finish.
I think that is probably what I will do again, yeah. Of course, when I say a set time frame, you ordinarily have 1 hour for a midterm and 3 hours for the final, and I doubled the 1 hour for the midterm, and if I double the 3 hours for the final, I mean, I don't know how anybody could sit for 6 hours staring at a bunch of these exam questions. So I think that even if I didn't put a time limit on it, you would probably be ready to just turn it in and walk away. So I don't know. I guess I'm trying to maintain as much of the pattern of what we would have had, even though this stupid pandemic lockdown has changed all of our patterns. If you guys have suggestions for things to do differently, just send me an email or drop in at office hours. And I'm hoping that this is all a one-time thing. We had a department meeting yesterday, and of course the number one question everyone is asking is, are we going to be able to go back to life as normal in the fall? And the answer we keep getting is we don't know. Apparently the university is going to be making some more final decisions in June. Two little ingredients that go into that discussion that I heard yesterday was that, first of all, people here are pretty nervous about the idea of throwing about 4,000 freshmen, or however many there are, all into one tight little dorm, and then, you know, taking them out 300 at a time to have them sit in some gigantic chemistry lecture. That's just seems like a perfect recipe for spreading the virus. And so that argues for not coming back to regular classes, at least not at the beginning of the semester. On the other hand, we did notice that Baylor University has apparently decided that, at least for the time being, they are planning on doing everything face-to-face starting on the first day of the fall term. So that plus our governor and lieutenant governor in this state are pretty gung-ho about reopening everything. So your guess is as good as mine at that point. All right. Do we have any other non-mathematical things to discuss? All right. Then let's turn to the new topic that we're beginning. This is the last topic from chapter 7. And I introduced it for you last time. These were the surface integrals that arise when you have a vector field. So I tried to explain a little bit about how they might arise and how you're intended to compute them, but I didn't do any examples last time. So let's do that, shall we? All right, so today's the 29th. Wow. So these are surface integrals that come from vector fields. And in the case of line integrals that come from vector fields, it made sense to talk about it even when you had a vector field in the plane, because a curve could exist in the plane. There's really not a whole lot to say about a surface that exists in the plane. I mean, it would just be a chunk of the plane. So we might as well just assume that this vector field lives in three-dimensional space. So I'll call that a capital F, and that's a function that's defined everywhere in three-dimensional space. And at every point in three-dimensional space, it gives me a vector in three-dimensional space. And of course, when you want to discuss surface integrals, you have to just have a surface. And that will be some sort of a surface that is a subset of three-dimensional space. All right, so the notation that you will see will be things like this. There has to be a notation that indicates the surface. And there has to be something about the vector field showing up in your notation. And then some sort of indicator that says, no, you're supposed to be computing the kind of surface integral that I discussed last time, which gives you a scalar valued function by taking dot products. So I guess this is the kind of notation that I will most frequently use. I think this is what the book and Quest are using as well. So except for maybe, I'm never really sure why they use the letter S in there for surface, I suppose. But I like to think about it as being, ultimately, it will turn into some measurement of area. I want to turn this into the kind of surface integral that we discussed earlier. Oops, sorry, I did exactly what I didn't want to do. The kind of surface integral we discussed, a couple of weeks ago, where we take a scalar valued function, multiply values of that times areas of little pieces of S, and add them all together. All right, and so the recipe for what this is supposed to mean is that this is calculated, the function little f here is going to be the dot product of the vector field f with a unit normal vector that I'll designate with an n, and I'm trying to be careful here to put arrows where the vectors are. Oops, I missed my, is that too sloppy? Yes. It's the integral of f dotted with n. So that will now be a scalar valued function, and just compute the integral of that with respect to area. So let's have an example that I'm going to compute for you in a couple of different ways. I'll first do one that's a little atypical, and it'll be atypical in the same way that if you go back to our line integrals, where I had a vector field and a curve, in this position right here, I had a unit tangent vector. And so I reached for one example where I knew how I would compute a tangent vector. And that was the case where the curve was a circle. In the same way now, I'll give you a sort of, it'll be a too simple to be typical example where I will know a good description of my unit normal vector on a surface. So here's my example. Let's have S be described implicitly as the set of points in three-dimensional space, such that x squared plus y squared plus z squared is equal to 4. So that's the sphere of radius 2 centered at the origin. And then I have to give you a vector field as well. So I'm going to do two examples with this same surface. One of them will be the vector field that, well, I'll write it out in formulas for you. And then I'll try to describe this with pictures. So this is a vector field which it's defined in every point in three-dimensional space. But for example, at the origin, this vector field is 0. So I don't know how to draw the 0 vector. It's just a dot. If I move over here to the point, let's see, one of the points on this sphere would be the point, where am I on? This is x, this is y, and z. So this here would be the point 0, 2, 0. And according to this recipe, then the force vector is 0, 6, 0, which points, it would be this vector that goes from the origin, pointing 6 units directly to the right along the y-axis. And as we usually do for vector fields, I'll draw that vector starting here at the point where I did the computation. So there's a nice long vector. It starts 2 units away from the origin and it draws another 6 units away. This vector field, I only care about how it behaves on the sphere, but of course, the vector field is defined everywhere in three-dimensional space, so you could draw the values of this vector field at intermediate points closer into the origin, where at the point 0, 1, 0, for instance, you'd get a shorter vector that is parallel to this one. Or you could go over here, I guess, to, I don't know, 0, 10, 0, and you draw this enormous vector sticking way out to the right. But our main concern is how does this vector field point when you're on points at the sphere? So I did one point that's on that sphere. I could do the calculation at another point, and you would see it points like that. I could try another point, and you would see it points like that. This one would point way down. So, of course, it's hard for me to draw one that's somewhere on the general point that's on the surface of the sphere. So kind of coming away from the origin, you point into the first quadrant somewhere, the first octant somewhere, to find a point that's on the sphere, surface of the sphere. And then it turns out that the vector f that you're trying to draw will always be 3 times the vector that points from the origin to where you are. So this particular vector field is always pointing directly away from the center, directly away from the origin. So it's the 3-dimensional analog of one of these vector fields that we've used as an illustration when we were trying to illustrate the concept of divergence. This is a vector field with a big sort of explosive feel. This is in 2 dimensions. Ours is actually in 3 dimensions. But you can see all of the arrows just diverging away from the center of the sphere. All right. Now, before I actually do the calculations, I've encouraged you guys, before you try to compute an integral, is try to estimate, what it is that what you think you're going to get as an answer, so you can judge whether or not your answer is silly at the end. Well, if you think about the kinds of word problems that I was associating to these surface integrals last time, one of the ones that I talked about was imagining chopping the surface up into little bits, and then over every one of those little bits, just drawing the mesh of a net. And you imagine that the vector field is indicating the flow of fish going across the net. And this is telling you how many fish are crossing into your net. And as you could imagine, in this case, you're going to get a lot of fish because you're, at every point on the surface of the sphere, the way I've just drawn the vector field is it's pointing directly out. So if the net is held along the surface of the sphere, the fish are flowing right into it, and they're all getting caught. So exactly the magnitude of this, I'll have to think about that in a few minutes, but at least you get the sense that this should be measuring something fairly big, in the sense that the vector field and the shape of your surface are kind of cooperating. They seem to be in sync. All right, so now let's try to make that more concrete. So the next thing that I would need to do is to figure out this function little f that I'm going to integrate over the surface of the sphere. And little f is the dot product of capital F with a unit normal vector. So we'll take the magnitude of this vector, but somehow reduce it by that factor of a cosine that accounts for the fact that the surface and the vector field might not be quite lined up. Well, in our case, they really are. In our case, there shouldn't be any diminution of the magnitude of the vector field. I mean, the magnitude of this, I'll let you compute that, is just 3 times your distance from the origin. And if you're doing that computation at some point that's on this particular sphere, that means the magnitude of this vector field is always going to be 6. You saw me draw a vector of length 6 here, but in fact, it's always going to be of length 6 as we take this vector field on that surface. And sure enough, I will get that number if I compute f dot n. Of course, I do have to come up with a unit vector that's normal to the surface at each point x, y, z. Well, here again, this is supposed to feel like what I did in the curve setting a week or 2 ago. If you want to come up with a vector that was tangent to the circle, what I had you realize was that the vector that goes from the origin out to any point on the circle is actually perpendicular to the curve. And in the same way here, if you take any vector that goes from the origin to a point on the sphere, then that vector will be perpendicular to the surface of the sphere. That's actually kind of what makes a sphere be what it is, that all the vectors from the center to the surface are perpendicular to the surface. So for my normal vector here, I might be tempted to just use the vector x, y, z. At each point x, y, z, this vector x, y, z is the vector that points from the origin to the point. So that would be a vector that's normal to the surface. Unfortunately, it's not a unit vector. The magnitude of this vector is the square root of x squared plus y squared plus z squared, which is the square root of 4. This is a vector of length 2. So to get a unit vector, I would have to divide by 2. And sure enough, now if you compute f dot n with this formula for a unit unit normal vector, you take the dot product of 3x, 3y, 3z with half an x, half a y, half a z, and what you will get will be, well, just 3 halves times x squared plus y squared plus z squared. Something is bothering me. Oh, no, that's right, yeah. And x squared plus y squared plus z squared for every point on my surface is exactly equal to 4. So this is 3 halves of 4, which will be 6. So as I said, that is the full magnitude of the force field, of the vector field, at every point on the surface of the sphere. There was no reduction. In this case, the factor of an extra cosine, that extra cosine factor is just a 1 because the vector field is pointing perpendicular to the surface. So that's great. This is the scalar valued function that I'm supposed to evaluate at every point on the surface. Chop up the surface, multiply values of this function times the area of a little piece and add them all up. Well, you're always just multiplying the area of a piece times 6. So when you integrate that function with respect to area over the surface of the sphere, all you're going to get will be 6 times the surface area of the sphere. And I guess, well, I don't know if you know, the surface area of a sphere is 4 times pi times the square of the radius, and the radius in our case is 2. So this is what I get for my integral. 24 times 4 is 96 pi. All right, so this is an example of a calculation that I could do in this particular instance because I could easily spot a normal vector at each point, and I could easily turn that into a unit normal vector. I knew the magnitude. I do have to point out that this was not the only choice of a unit normal vector at the point x, y, z. There are precisely 2 unit normal vectors. I mean, if you imagine the surface going through space and you pick any point on the surface, then there are exactly 2, well, there's one line that's normal to the surface, even a curved surface. At each point, there's only one line that's normal, and if you need a unit vector, you can pick either that one or that one, and they'll be negatives of each other. So I've illustrated the case where my normal vector is the one that goes from the origin to the point x, y, z, but you could just as well have chosen the unit normal that goes the other way. That would point from the surface back to the origin. And of course, the formulaic description of that normal vector would be minus x, minus y, minus z. It's still of length 2. So everything would be the same except for the presence of a minus sign. So this would be a negative 6 instead of a 6, and the whole integral would turn out to be negative 96 pi. So which of them is right? The answer is they're both right, mathematically speaking. If you tell me which one of those normals you want, then I will compute this integral and I'll get a number. If you change your mind and say, no, I meant the other unit normal, then of course you'll just pick up a minus sign in here. Well, which one did you mean? It kind of matters whether or not you're measuring the flow of the fish or whatever that way or this way. If you were, I was having you imagine a fishing net here before, but if you think of this with that other sort of physical model that I was describing, where the net is replaced by a pipe, well, do you want to count the fish that are flowing into the pipe or the fish that are coming out of the pipe? In the one case, you want to be using the outward facing normal, because then this dot product would be a +1. I mean, the cosine factor would be a +1, so you'd be counting as a positive every flow of every fish right through that little disc on the sphere. And in the other case, if the fish are being ejected into the sphere through the pipe, well, then you want to count a positive number only when a fish is swimming into the ball through the sphere. So in that case, you'd want to be using the unit normal that points towards the origin. Those are the ones that you want to count as a positive. Okay, so the question of which unit normal you want has to be decided based on which one of the two unit normals corresponds to whatever it is that you're physically trying to measure. Okay, any questions with this one example? All right, now.
Doctor,
yes, go ahead.
Sorry, I just have one question. So in this problem, you kind of, it seemed like you just reasoned that the normal vector was just XYZ from like some prior knowledge, but like how, in general, how would you determine the n unit vector?
Yeah, that's a very good question, and that's precisely why I've been calling this an atypical example, because we have special geometry at our disposal that lets us figure this out. So I'm going to do one more atypical example with the same surface S, but you do have to concede, yes, in general, it's hard to figure out the unit normal. You know how to do it for a sphere, and from early in the semester, you guys know how to do it if the surface is just a plane. You guys remember how to get a unit normal vector for a plane. But beyond that, nothing. So that will be my next example after this one that I'm about to do, okay? So that's a good question, but I'm not quite ready to answer it. All right, what I did want to do next, though, is to show you an example where it'll just feel different in a physical sense from this one, because this vector field is kind of exploding away from the outside, from the inside out. This is kind of a big bang taking place, and just like in the Hitchhiker's Guide to the Galaxy, it's all about the fish. So long and thanks for all the fish. So fish are apparently being created, or they were all in here and they're trying to escape or whatever. But you have this sense that there's something in there that's coming out. And when you calculate this surface integral, you get something that's positive. So I want to do something different now. For my next example, I want to keep the same surface. But for my vector field, I want to have one whose flow looks very different. So suppose that I have a flow that's just equal to, let's have it just be something like this, 2, 3, 4. So you'll notice there's no x's or y's or z's in here. This is a constant vector field. At every point in three-dimensional space, you're getting exactly the same vector. I don't know, let's see, from the origin it points 2 units this way, 3 units that way, and 4 units up, so it's kind of coming out like that. But I'll draw a carbon copy of that vector everywhere in space. So that's a steady wind, it's just, or it's a stream filled with fish that are all just happily flowing past you. It's an incompressible liquid in this case, something like that. And the sphere is still here. But now, I mean, what do you think is going to happen? You're going to be putting little fishing nets at each point on this surface of the sphere. And what's happening at each point on the sphere is going to be different depending on where you're standing. Right here, you still feel the fish coming into your net, and you're like, oh yay, I'm going to eat fish tonight. Whereas up here, there's a little patch where the picture just looks like this. Your net is like that, and the fish are just swimming directly parallel to it, and so they're kind of oblivious even to the presence of your net. And over here, the fish are swimming, I mean, you feel like you're catching them on the other side, but if you use that model of fish coming into and out of pipes, this is where there's fish being sucked in to a pipe, but maybe that same pipe is coming around here and spitting them back out. So I hope you're getting the sense that the net number of fish that you're catching by this spherical net is going to be 0. And I want the calculations to show that. So how would we do this? Well, I don't know. It's the same deal as before. I have to calculate that scalar valued function that I get by taking the dot product of my vector field with this unit normal vector. I can use the same unit normal vector that I had before. Of course, I did have two choices, but let's just choose the one that points outward everywhere. So people would just say, when they present you the problem, they would say, let n be the outward pointing normal vector. So here's what you're going to get now. You're going to get just x, no, not a vector, x plus 3/2 y plus 2z. So now you have a scalar at every point x, y, z on the surface, on the sphere. And okay, now you're just integrating a scalar valued function across the sphere. Take the sphere, chop it up, multiply the areas of the pieces times the values of this function. Now, here's what you should realize. This function is going to return a positive number, of course, if x, y, and z are positive. If you're in the first octant, this will be positive. But if you're in the whichever number octant it is, where x, y, and z are all negative, well, this is going to be the same magnitude, but it'll be a negative number. So if you split the sphere up into two parts, the part that's sort of this way and that way from this plane. So in here, I'm drawing now the plane of points where x plus 3/2 y plus 2z is equal to 0. Well, if you're on one side of this plane, then this left-hand side will be positive, and if you're on the other side of the plane, then this left-hand side will be negative. The place where the left-hand side is equal to 0 splits space. And so you'll be having positive contributions, sometimes large and sometimes small, as for all the points on the hemisphere that's over there from the plane. And if you're over there from the plane, then all the points on this hemisphere will make this function be negative. And by the way, it really is a hemisphere. This plane passes through the origin, right? 0, 0, 0 will make this equal to 0. So the origin is on this plane. This plane goes right through an equator. Well, you would call it a great circle of the sphere. And so you could argue just by symmetry, and you do have to be careful about this. Some of you got ahead of yourselves thinking about symmetry on the exam. By symmetry, it is true that the integral of this function over the sphere is equal to 0. And that captures what we were kind of expecting from the physical reality of the situation. And if you're a little dubious about the math, about my jumping to this claim of symmetry, you can figure out the value of that surface integral. Just like every surface integral, you have to begin by choosing a parameterization of your sphere. So you might use, for example, x, y, and z being given by that formula from spherical coordinates. Since you're on a sphere that's centered at the origin and the radius is 2, every point has a row coordinate of 2. But then the other two coordinates can serve as your parameters in a parameterization. Usually this would be called phi, but I want to stress that I'm just treating it as a parameter, one of my two parameters. So that would be the parameterization that I guess I would use. And so then I would say, okay, let's change the three parts of my integration formula. My integral of f over the sphere will be the integral of, well, I'm not going to bother substituting this in, but it'll be here, 2z is 4 times the cosine of u plus 3/2 of a y will be 3, etc. Okay, there's all of that. And then your new domain would be the combinations of u's and v's that you need to get the entire sphere. You know that you need the u, it's usually called phi, to range from 0 to pi, and the v, usually called theta, ranges from 0 to 2 pi. And then finally, you need to figure out your differential. And I remind you, the way you would get that would be by taking your parameterization t and taking the derivatives with respect to both u and v, taking the cross product of those two vectors, and computing the magnitude of that. So I won't bother actually finishing these calculations in this example because I kind of already know what the answer is going to be. I get it either by just purely mathematically, I get it by thinking of a symmetry of the geometry here. And physically, I get it as a 0 because I know that I'm gaining just as many fish as I lose. But I do encourage you, if you're, want to practice with computing these surface integrals, go through all of these calculations, and that would be how you could actually evaluate the surface integral. After all, that's what we're going to have to do in general for these problems.
Can I ask a question?
Certainly.
Why did you multiply 2, 3, 4 by, or dot product, I guess, by x, y, z over 2?
That's the unit normal, just as in the previous example. I'm still using the fact that on the sphere, I have an easy gift from geometry that lets me predict what a normal vector would be. And then with the factor of 2, it turns into a unit normal vector.
Well, wouldn't the square root, because if the magnitude of x, y, z be like the square root of x, y, z over. Yeah, I did the square root wrong. My bad.
Yeah, did you get an x? You had a 4 instead of a 2?
Yeah.
Yeah. No. It's a square root in there. Remember, the magnitude of the vector is the square root of the sum of the squares.
Yeah.
So this is a sphere of radius 2. All those vectors have a length of 2, and that with the 2 in the bottom, it's a unit.
Yep. Thank you.
All right. So now I want to do a similar one of these, but I want to address Malik's question of where the heck am I going to get the normal vector if I don't have such a nice kind of gift from geometry to help me identify these normals. So this is actually the typical situation. I went from typical to atypical now. So let's have a different surface that's not a sphere centered at the origin. So let's use S to be, let's say, the graph of some quadratic polynomial. So I would take the set of points x, comma, y, comma, z, such that z is maybe equal to x squared plus y squared. So that surface, that's an unbounded surface for just a moment here. And that graph, I hope you know that the graph of this one is that paraboloid. So you need a bowl that's touching at the origin in R3, and it comes up away from the origin, parabolic dish. A bowl, I just always call it a bowl. In order for our integrals to make sense, we do have to have a bounded chunk of this surface. So let me put a bound on this. Let's have the x squared plus y squared be less than or equal to 4. So that means I'm going to take the portion of this paraboloid that lies over the disk of radius 2 centered at the origin in the xy plane. So from a perspective view, here's that disk. It looks more elliptical in the perspective. So down there, let's have a name, capital D, for the disk, but our surface floats directly above that. Each point x comma y gives us a point x comma y comma z, where the z is computed by that quadratic polynomial. There, you see a bowl, I hope. All right, now, you can see that at each point on this surface, there's a pretty clear direction. There's one of the directions that points kind of into the bowl. It's pointing kind of up. And the one that points out of the bowl is pointing kind of down. So let's have this be a typical problem where they would not only give you the surface, but they'll try to indicate which of the two normal vectors is relevant for the physical application that they have in mind. So let's just say that I want to do this with an upward pointing normal. And I have to give you a vector field, of course. Let's not go too wild right away. Let's just take that constant vector field that we had before. All right, so now it's not so clear whether I'm going to get something that's positive, negative, or 0. I mean, I could draw that same plane that separated out the places where the dot product would be positive from let's say it this way. That plane that I drew, that was a plane. Well, it was the plane through the origin that actually was perpendicular to this vector field. This particular vector field is constant, so I have the same vectors everywhere. But in particular, I can find a plane where these vectors are all perpendicular to that plane. And in this case, okay, that would indicate places where this function is going to give the little f will be positive versus negative. I can't quite see how that's going to mesh with this paraboloid. But I do kind of feel like more of the paraboloid is on one side than the other of that plane. So I don't know, we'll see. Well, we do have to try to get the function to integrate. And to get the function to integrate, I got the vector field, but I need the unit normal. I got to have this function to integrate because I know what I'm going to do with it at the end. I will laboriously have to go through this stuff. I will pick out a parameterization of the surface, and then I'll plug in some formulas. Of course, when I start to do that, I will have to compute this fudge factor, the thing that accounts for the stretching of areas, based on whatever parameterization I choose. So I'm going to defer the question of the normal for just a second and say, let's try to get ready with the parameterization that we're going to use so that we could carry out a surface integral on this surface. Well, what parameterization can we use? This surface is the graph of a function of two variables, and for that setting, I've encouraged you guys to just reach for the, I guess I've been calling it the cheater's parameterization this semester. I don't know why I've been using that term. But this is the parameterization that you can use on the graph, on the graph of a function. Maybe I should use u's and v's. You take any point in the UV plane and you get a point in XYZ space by just copying the first two coordinates. U is synonymous with X, V is synonymous with Y, and then of course Z is going to have to be U squared plus V squared. And the portion of the UV plane that I need to get that whole bowl would be, it's the set of pairs of U's and V's such that U squared plus V squared is less than or equal to 4. With this parameterization, you know what I'm going to have to do in a minute. I'm going to have to compute these vectors, the two columns of the derivative of this function. Why did I put that? It should be U and V. Sorry. What I meant to say is that those are X, Y, and Z outputs. But these are the three outputs computed in terms of U's and V's, and so the derivative of this function from R2 into R3 is going to have the three gradients as its rows. Here's the first gradient, here's the second gradient, here's the third gradient. So this column is, this is T prime. This column is the T sub U, this one is the T sub V. And you've observed in the past that when I take this kind of a parameterization from, to get the graph of a function, the cross product, it turns out to be pretty easy to compute. The first component is just exactly a one, no, the first component is minus 2u. It's the partial of this function with respect to u. The next is the partial with respect to v, and it's the third one that's just a 1. Okay, so this is the next thing that I would write if I were doing a surface integral over this paraboloid. If you had given me a scalar valued function, I'd be saying, oh yes, I need to have this fudge factor in here that takes account of the fact that areas are distorted when you go from the UV plane straight up to the surface. The areas get bigger. You're stretching things by a factor of exactly this much. Okay, yeah, cool. However, T sub U and T sub V, these two columns, those are vectors that will actually be tangent to the surface. Exactly what they are is, you're going to stand at a point in the UV plane, that's this disk at the bottom, and go little units parallel to either the X or the Y axes, and try to copy those straight up here. but make them, when you go straight up, you'll be trying to make a vector that's tangent to the paraboloid. So you end up with the two of these. This little rectangle below becomes a parallelogram that's tangent to the paraboloid, and this is its area. However, in addition to knowing its area, which is useful, you also know that when you take the cross product of those two tangent vectors, you're making another vector that will be perpendicular to both of them. You're perpendicular now to both of those tangent vectors. So you're perpendicular to that little parallelogram, which means you're actually perpendicular to the surface. So this right here can be a normal vector. And that is just the kind of thing that I need in this setting. Of course, I need it to be, right here, I need it to be a unit normal vector. So what I'm supposed to do is to take the vector field that describes capital F at each point, that's a vector, and dot it with the unit vector, a unit vector that's normal to the surface. Well, I can put in the minus 2u comma minus 2v comma 1, but I'll have to divide by this length of the tu cross tv. I'm sorry, that's a little crunched in there. I should have left a little more space. But, you just multiply all this out. When you compute the dot product, you will get minus 4u minus 6v plus 4. And that's your numerator, and your denominator is this ugly looking square root. And that now becomes, this is your function f. That's the scalar valued function. This is a number now, not a vector. That's your scalar valued function that you're evaluating at each point on the paraboloid. And so, here you go. You want to start computing the integral? Well, what you would need to do is parameterize the surface, and I did that. And the reason you parameterize the surface is that you now think of this as a parameter, as an integral over your parameter set D, that's just disk. And what you're going to evaluate on D is, you're supposed to take this function and replace any x's and y's and z's by the corresponding formula in terms of u's and v's. And you'll notice that there are no x's and y's and z's left in here. That's special to this example because my vector field had no x's or y's or z's up here. If I had some up there, they would still be here and they would still be involved in this formula. But this would be the moment that you would get rid of them. Replace every x by a u, every y by a v, and every z by this thing. Then you would have to multiply by this magnitude of tu cross tv and integrate with respect to u and v. But that is exactly the thing that I've already put into this denominator. So really, that factor and this factor will cancel, and all I need was the part that I got by taking the dot product of the vector field with this normal vector itself. You don't have to worry about whether it's a unit vector that's normal or not. I get minus 4u minus 6v plus 4, and that is the thing that I integrate with respect to u and v over the disk. Now, since it's a disk, if I were you, I would switch to polar coordinates and make this be an integral as the r goes from 0 to 2, the theta goes from 0 to 2 pi. The integrand could be written as minus 4 cosine of u. I'm sorry, I shouldn't use u. Minus 4 times, minus 4r cosine of theta minus 6r sine of theta plus 4. And of course, when you switch to polar coordinates, there's an extra factor of an r. So this would be the iterated integral that I need to compute. It's actually pretty easy. When you integrate the cosine or the sine over the full period of thetas, that will just turn into a 0. And if you integrate the constant with respect to theta for that length of thetas, you'll just get that length times 4. And that still is multiplying r times dr. And so the antiderivative is r squared, which at these endpoints is a 4 there. Sorry, I'm sort of mumbling to myself, but I believe the answer is 16 pi. So this is actually your typical example. Given a surface and a vector field, you better parameterize the surface first, because you'll need that for two things. You need to know about this fudge factor for lengths, but you also need to know a unit normal vector. So this is a normal vector. Don't bother scaling it to turn it into a unit vector if you remember to also not bother to put in the fudge factor for the areas. Just compute the dot product of your vector field. This right here is F dotted with the TU cross TV. And then now you'll just have a function, a scalar valued function that you integrate over your chunk of UV space, and you'll get a number. I am officially out of time, so I will just ask you to do one thing. How do you know that you've got an upwardly pointing normal? Remember, there was always going to be two choices of a normal vector. Did we get the right one, and how do you know? All right, you have to figure out what upward means. Upward means that you have a positive z component. Your third component needs to be positive. That's when I would call something upward as opposed to downward. And here's our third component of our normal vector. It's got a positive 1 as its third component. So I think we made the correct choice here for our normal vector. Scaling it, shortening it to a unit vector, that won't change the fact that that's positive. But the word upward in this case is reflected in the fact that that was a positive number. So we got the right thing measured here.
So if we compute our normal vector and we get like the downward pointing one, can we say, oh, we choose the upper pointing one, which is the negative of that?
Correct, correct. I mean, what it would amount to is just maybe taking TV cross TU, you know, that would just reverse the roles. But everything else that I said about who's perpendicular to whom, TV cross TU would do the same thing. It doesn't have to be in alphabetical order, by the way. You know, I could have changed the names of the variables here. Why don't I call that V and call that U, and then this would be V squared plus U squared. And then if you literally wrote TU cross TV, well, you would have these two things in the opposite order, and that would change the cross product that you compute. So, yes, so don't worry about it. Just find a normal vector by computing this thing. And if it isn't the unit normal vector that they wanted, just change the sign. In fact, you could go all the way through at the very end, just say, wait a minute, did I have the correct normal vector or the opposite one? And if you have the opposite one, then it's perfectly fine to just put a minus sign in there. Now, I have to caution you, sometimes when you do all these calculations, what if over here you had it, that turned out to be just a U? Then you have to be careful. You would have the correct normal vector on the places where U is positive. U I had was my synonym for X. So that would mean that on this half of the disk, I've got the appropriate normal vector. On the other half of the disk, I'd have to use the other one. So you'd have to split your integral up into two parts. Okay, so that'll never happen to you in a case where you have the graph of a function as your surface, because in those cases, you'll always just get a 1 right here. But in a more general setting, yeah, that could be a problem. All right, any other closing questions on that? All right, guys. We can do more of these examples with you together on Friday, but I also want to start Chapter 8. Chapter 8 is where the great theorems are, and so I want to make sure we get that right. Come to me on Friday with questions if you like, otherwise I'll just start you in on the papers. All righty, I'll see. Question?
Yes. So here you're using the change of variable theorem twice, right? Once with the TU cross TV and another time with the R theta.
Yes.
Okay. Yeah.
I mean, you could combine them. You could have been more clever in the parameterization. You could have had T of UV be U times the cosine of V, comma, U times the sine of V, comma, U squared. And that would have worked as well. That kind of combines the two applications.
Okay. So yeah. You're doing the R's and thetas once with the first parameter, with the first parameterization.
Yeah, but I mean, you know, it's the same as Back in Calc 1, where you were first being introduced to the U substitution, you may have noticed that sometimes you do a U substitution, your integral got easier, but it's not easy enough. And so you had to do a second U substitution. Well, now you probably call it a V substitution. And then it got even easier. Well, you know, anytime you do two substitutions in a row like that, you can look back and say, oh yeah, I could have done it all at once. By just kind of combining the formulas, you see what you could have done as your U substitution at the very beginning. But you know, if you didn't see what would have been super simple, if you didn't see it all in one step, that's not bad. Just do it as two separate steps. Same thing here.
All right, thanks.
All righty, guys. We'll see you next time.